Said by Gunnar, I think it's better to restart, and then the second part of the meeting is more general, it's more dedicated to science, and I think this is one of the most interesting aspects. So do science with the sun, and so not only focused on the instruments, and then I will acknowledge in advance all the people that accepted to talk about this. The first one will be Peter Wiltoff from the Swedish Institute of Space Physics. Please, the floor is yours.
Okay. Shall I take the microphone? Or?
Yes.
Yep. Thank you. Okay. Thank you very much for inviting me here today. I will talk about space weather machine learning. And I think the connection was via Marco and Alberto, and actually via Mauro Messarotti, another Italian guy who's been working in the space weather field for many, many years. So I guess that's the connection here. Two exciting topics, especially in the recent 10 years. Both topics has really grown in interest, and there's been a lot of activities. So very short about the institute climate. Swedish Institute of Space Physics, or IRF, Institute for Rymdfysik. We have 4 offices that are quite equally spaced in latitude, about 450 kilometers between offices. And we are about 120 people in total, spread over the Kiruna, which is the head office, Umeå, Uppsala, and Lund. And I'm in the Lund office. It's very nice also if you have instruments and magnetometers or cameras and ion sondes and so on. We have these 4 offices to serve them. So, space weather. This is an old cartoon that I like very much because it's a very good summary of everything that's related to space weather. And you can see all the different effects and on technological systems. For example, you have earth currents down here where you can see the power electrical grid or pipelines. You have effects on the global navigation and satellite systems. HF radio, for example, can be important for flight. Atmospheric drag, maybe you heard about this SpaceX, 40 satellites lost due to this because of the smaller geomagnetic storm. Effects on astronauts and so on. So it's really a big, complex system, especially when you take into these technology effects. So essentially we have the sun, which is the cause of all these effects. And we typically talk about, the biggest things are talking about solar flares and coronal mass ejections. And especially when we talk about coronal mass ejections, it takes about 1 to 2 days for the fast ones to reach Earth, maybe a few days more for the slow ones. And then eventually they reach a spacecraft that is located in L1. In this picture I show the A's, but right now we're using the Discover spacecraft instead. And it measures continuously the state in the solar wind, particles, magnetic fields and so on. And then maybe 30 minutes later from this spacecraft, you get the interaction with the Earth magnetic field. And this is a sketch of the Earth magnetosphere with all the magnetic field lines that are pulled out. And you get this interaction between the solar wind and the Earth magnetic field that drives a major part of what we call the space weather. Just very shortly about a few interesting events that are space weather events. In May 1921, these are actually solar observations. So this is an image from the Greenwich Observatory in the UK in May 1921. And this is a drawing from Mount Wilson Solar Telescope in US. And this produced a big CME. And it's been described, for example, in 2 papers, one by Henrik Lundstedt from 2015 and Mike Hapgood in 2019. And it had a worldwide consequences. But one of the effects was a fire in the telephone exchange in Karlstad at this time. So this is a black and white picture of the station inside. Maybe it's hard to tell what it should look like without the fire, but it was knocked out. And One of the problem was that when they called the fire department, of course, they couldn't get on the line because the exchange was down. So that was another side effect of this. March 1989, that was also a big event. There was actually physical damage to a transformer on the east coast of the US. You can actually see the burnt windings here on the transformer. And this has been also well documented, this event. And we have a lot of different, quite large events. This is described in Magnus Wijk paper from 2009. Another one, October 2003. The movie you see here is from the SOHO telescope. It was launched in 1995, but it's still active. So what you see is images or movies of the solar corona, and when you have these coronal mass ejections. And during Halloween in 2003, there was a big CME, and it actually led to a major blackout in Malmö. And there was a lot of consequences from this also. They have say in this article about 20 trains affected, 7 people trapped in elevators, that's serious. Collisions between car and the fire engine and so on. But this is, so that was the big CME, and then you can see all the particle radiation actually going into the camera of the telescope.
Can I make a stupid question? So even Tesla car self-autonomous drivers.
Yes, if they rely on GNSS, for example, yes, of course.
There is no warning when you buy Tesla.
That I don't know. Okay, so this is just one effect which we know of and which we see, and this is I mean this event in 2003 was a power line that was disconnected because of security reasons. It was disconnected. So this kind of disconnections is what we usually say is driven by geomagnetic-induced currents. So this is the technology side. I usually divide it in this way. Then you can of course have models of these GSEs. For that you need a power grid model. And then you can also have observations. So that's observations that could be in the control room of the power company. But you can also measure these geomagnetic-induced currents, or you can measure what they call harmonic distortions in the systems. Then we come to the physics side. What is driving these GSE? I will not go into all the details, but essentially we have this magnetosphere-ionosphere system, and it uses changes in the ground magnetic fields, and then of course also in the electric fields. We can have models of these electric fields, and to drive these models we need like conductivity maps of the Earth, and we need ground magnetic field measurements. So in this case you can do like monitoring and post-event analysis. Then if you want to do predictions, you can go out to these solar wind monitors. So for example at this L1 solar wind monitor, then you get approximately 1 hour, maybe 30-minute prediction lead time. And then you need some kind of solar wind magnetospheric models. And you need observations, which is actually the monitors itself. And then if you want to go further, say like a day prediction, then you actually have to look at the CME. And for that you need coronal graphs at least. And then you can, look at the CME, try to have a model of the CME and so on. And if you want to go even further, say a couple of days, then you have to look at these active regions, and then you have, for example, magnetograms on the sun. This is the observations, and then again you need models. But this is quite interesting because this is just one effect of technology. So there's a chain of events that are interesting. And in this chain you can actually see there's no flare. So the flare is not really important for this technological effect, but the CME is, of course. So something about prediction models, because that was the space weather part. Now I'm going into this machine learning part. One way that I like to view it is that you have some input space. It could be the whole universe, and you can look at the stars, you can look at the constellations of stars and so on. And you have some target space. For example, you want to predict geomagnetic activity, or you want to predict this transformer disconnection. And of course, you have fully unconstrained, you can have all possible imaginable effects going from one space to the other space. But of course, we want to restrict this. We want to identify what is the actual, hopefully, cause of these effects on the input space. So these could now be magnetograms or the solar wind data and whatsoever. And then you want some mapping, a function that goes to this target space, which could be our geomagnetic activity. And of course, one way to do this is to look at the physics models. Usually what you have is a set of differential equations. So that's how you squeeze this space down to something that is actually relevant. And then from the other part, you have this machine learning where you actually look at the data and the distributions and you try to find this function instead. It's two different approaches. So this is just one example of these kind of physics-based models. It's a model that was originally proposed by Dusan Ostersill. It's an MHD model, and this one is implemented by the Met Office in the UK. So here you put in the CMEs, and then you can trace them through the solar wind and how it interacts with Earth. So this is very important. On the other hand, if I would just want to mention something very shortly about these machine learning techniques, you can go to Wiki and you can see how they define it. But it's again, it's about finding functions or mappings from the data. And there are some theorems that are really building behind this. If you have what is known as a static neural network, without going into detail what a neural network is, but they are universal approximators, which means that you can approximate any given function. And this is just one illustration of a step function that is modeled by a small neural network. Then they came up with the dynamic neural networks, so now they are looking at things that evolve in time. And these are the recurrent networks, and they are also universal approximators. Other types of machine learning I will not go into. There's a really big zoo of different algorithms, but another interesting also known as Gaussian processes. And now you can actually feed into these systems not the functions of the mapping, but what kind of the function should look like. I mean, should they soft, should they sharp, steps, and so on. So, an example of a machine learning model. This has been running at our institute for many years now. It's the forecasting of a geomagnetic index called KP, which is used in many different space weather applications. So here we feed the solar wind data into a neural network that makes these predictions. And it runs in real time, and you don't need any like supercomputers or anything, because it's really these algorithms are really fast when you go in this prediction phase. So something very interesting that's been evolving also through the last few years is what is known as physics-informed neural networks. So this is a way to take, for example, if you have a set of differential equations, and then you can connect them to these machine learning algorithms. So now you have the good from both worlds. So you can put in your pre-knowledge and you can combine it with these data searching algorithms to come up with these function mappings. So if I go back to this picture I had before, we have, for example, our differential equations, and we have our machine learning approach to reach these kind of predictions from input space to output space. But actually, when we develop machine learning, we don't do it completely blindly. We actually use information from physics to see where we should go. But this takes it now to another level where you actually combines this part with this part, and these are all known as PINs, or physics-informed neural networks. And it's described in this paper, and then there's been applications of this. So just to give some, it's not exactly a physics-informed neural network, but it's something that connects to this kind of thinking. And I don't know how many of you know about the ring current, but it's actually just where you have particles circling the Earth, and they generate a magnetic field on the ground surface. And when this ring current increases in strength, the magnetic field decreases at Earth around the equator. And you can express that with a very simple differential equation. So you have the time derivative of the ring current. You have some injection function, which depends on the solar wind, and then you have some kind of decay of the ring current. So when you get solar wind injected, DST goes down, but then when the energy injection from the solar wind stops, the DST decays back again. Of course, that equation is only approximate. So what we did was to take a very small neural network, which is this kind of recurrent dynamic networks. It means that they can learn time series. So what you see here is just the solar wind coming in here, go through the networks, then you have some feedback connections, and then you have this output, and then this is another way of showing these kind of predictions. But actually, if you take a very minimalistic neural network, which is this one here, it's actually a differential equation, which is of the same form as these equations. So now you can suddenly interpret this tau, for example, the decay term, when you look at this model. This is not the same as the physics-informed neural networks, but it connects the two worlds, so to say. Yeah, actually, if you want anyone interested in this, you can actually, there's a GitHub repository where you can look at this simple model for this kind of differential equation. Some machine learning in space weather. There was a workshop a few years ago organized in Amsterdam. That was actually in 2019, but on the webpage they tell about the next workshop. It was organized by another Italian guy, Enrico Camporeale. So you're all over the place. Let's see. There was a big EU project a couple of years ago known as FLAREcast, where they used these machine learning techniques for flare forecasting, very much based on solar magnetograms and identifying important features and so on. There's been many different approaches. For example, if you want to look at ground magnetic field or geoelectric fields, and they used something called LSTM, which is another kind of recurrent neural network. And then there's an example of these kind of physics-informed neural networks to look at the radiation belts from 2022. So to be able to do all these things, we really need a lot of different observations. And this is from the Heliophysics System Observatory. It's a link to the NASA page is down here. And as you see, we have a lot of spacecraft that are really crucial for this kind of space weather monitoring and modeling. And especially the stereo spacecraft, SOHO, ACE, and SDO, because they continuously measure this kind of data, either the corona, magnetic fields, or in the solar wind. And then, of course, there's a lot of different observations on the ground at Earth. And as I mentioned, I've shown some movies of the SOHO, which is now very old. It was launched in 1995, I think. There are plans of launching a new satellite that will more or less replace SOHO, which is known as the Vigil. It's an ESA project, which is very important. And it will place the spacecraft in the L5 location. Here is L1, so this is where SOHO, Discover, and ACE are placed. But this will be placed in L5. And that's very interesting because now we will look at the sun from the side. And one of the difficulties when you have coronal mass ejections is that when we view it from the Earth, if it's propagating towards Earth or away from Earth, it's very important to know, but it's also very difficult to see this difference. And this is somewhat similar to where the Stereo spacecraft were a few years ago, where this L5 location. So we have data from previous observations like that. So my last slide. Solar radio I know very little about, but it's exciting to learn if there are some new ways of observing the sun and using this kind of information to make any kind of space weather or at least the potential for space weather predictions and so on. And I know there are some ideas of the flare prediction where you can actually look at these wavelengths and you have some kind of precursor of the flares. That's why I asked about the lead time about this, and also about what is the physics behind it. Halo CME, the Halo CME, this is when you observe the CME as a ring that expands out from the sun. And then it can, as I mentioned, it can either be Earth directed, which is interesting for us to know, or it's directed the other way. But that can be quite tricky. But there's also a case study where they actually used different types of frequencies, but still radio observations of this event. And then also CME arrival time. We want to know how fast the CME is, because usually fast CMEs, they usually give the biggest effects. The problem is we have no observations between the sun and Earth. We only have models. And models it's very nice to have these models, but there are some quite problems to understand when the CME actually will arrive. So could we ever have the possibility to actually follow these CMEs from the sun to the Earth? That would also be fantastic. So that's all.
Thank you very much. Question? Wow. Please. Please.
What can parameters go in the Q function over from which spacecraft?
You mean this one?
Yeah.
Yeah, this is the solar wind coupling functions, and there are many different suggestions about this. I can't remember. I can't remember this paper by Paul O'Brien and Robert McFerrin. But usually, of course, you need the BZ component, or you could the electrical field. So you take the BZ times the velocity, so you get the electric field. So that's for sure.
And this is
But and then also this is you see it says DST star. So this is actually the pressure corrected DST. So what you take, you remove the solar wind pressure from this equation first, and then you handle the dynamics here, because the solar wind pressure is immediate. DST changes directly with the solar wind pressure. But then you have the dynamics in this pressure corrected DST. But electric field, and then you can have different combinations.
So you need some solar L1.
Yes, exactly. Nice to have a question about that.
I thank you for this very interesting talk and approach. Really connecting the scientific part with the more operational services part of space weather. It's mostly a comment what I would like to do. You cited the very many different projects on machine learning, including your own effort in your institute. I wanted to underline that in Italy we have an expertise in machine learning and in flare forecasting, because in the project of Manolis Georgoulis that you cited, the algorithm part and the software part was done by the University of Genova. Have Professor Michele Piana there that has worked for many years. Have also some other projects, also with the Italian Space Agency, working on this stuff. So I think it is a good point also to interlink these efforts maybe in the future. Yeah,
absolutely. I know I don't know if it was on this web page. Let's say, not web page. Let's see. No. It was actually the first artificial intelligence data analysis school, AIDA, for heliophysics. That was organized in Italy, in Bologna, and it was Giovanni La Penta. But he's in Leuven,
Yes, I
Yeah,
know.
exactly. Yeah. So, but absolutely, this is. I know you have a very
Okay.
strong.
Thank you.
We just very quick comment on that. Thank you, Peter and Christina, because this is the point. With the Stanglish archive, we start to have quite a lot of images to correlate the different features in our images, not just precursors of flare, but also dark halos, coronal holes, many features that seems related, polar brightening. We have some hypotheses about the physical interpretation, but we are weak about the machine learning technique that now will be needed to even just with a first approach, just using the radio data before to put them then we will be glad to put your expertise together to start with play also with our data and in perspective of you, obviously also of Solaris that will have a lot of data to correlate. It's not just look at the image because the image will be so a lot of number.
If there are no other questions or comments, let's go to the next speaker, which is Cristina Blonaghi, which is she was working at WINAF for many years, and now she is working at the Italian Space Agency, ASI, and I also forgot to acknowledge the support of ASI, which is also the main sponsor of Italian National Space Day, which is actually under the umbrella of the ASI.
Thank you. Thank you very much.
I'm opening up.
Thank you.
Let me see.
Yes, this is one.
It is the one. Ah,
Oh, no.
what happened
Maybe
to
you
the
have
screen?
put full screen. Oh.
Disappeared. Now connect.
It's coming.
It's coming.
Yeah.
I didn't notice it disappeared. Are you happy with this?
Maybe you can put the full screen.
How do I do that? I'm not so good at this.
Presenting.
Yeah, but that is because I am in that. Remove that one. I move.
You have to leave this part, maybe home. I'm working on Macintosh.
Yeah.
I'm not very familiar.
Okay. Anyone who knows how to go from a
screen?
PDF to full screen? I forgot. Yes. How?
View, but where is view?
Where is view? That's
Maybe
my problem.
home. I would go here. Home, maybe.
Home.
No.
Home is not so good.
No.
Oh, terrible. We go back. What happened? We'll go. We are not. We don't want to go home. We go back. That's fine. Presentation. Okay. Have a look at that now. Ferrets. Research. No, Acrobat would be better. We kill it. We'll see if we can. We have Acrobat. I would hope.
You can write and open with.
Det kunde ha gjort. Let's wait. Så. Det går tillbaka. Right click it. Open in Acrobat. Open with. Merci.
Yes.
Okay. We cross our fingers.
Yeah. Otherwise, I can do it also without the full screen.
My problem is that I don't get the Acrobat to start running. For reasons unknown. Here it is. Menu, open. Here it is.
Yes.
Perfect.
Okay, and now this is full screen?
This is full screen.
Okay.
I will capture that.
Yeah,
Maybe.
as you prefer. So, again, so good evening, everybody. Thanks to Augusto and Cecile for this invitation today. So I'm a researcher. Yes, I'm a researcher in the Space Agency, and I work in the Policy Direction of Science and Research. And today I will talk to you about a project that we have, and it is dedicated to space weather research. So this is the outline of my talk after a brief introduction, mainly focusing on the multidisciplinary nature of space weather science. I will place our efforts in an international frame in relation with other efforts in Europe and in the world. And then I will describe our project, which is dedicated to the development of space weather infrastructure, a scientific space weather data center in our agency, a project in collaboration with INAF. And then finally, I will present some concluding remarks and points of further discussion. So when we talk about space weather, in reality, we do not refer always only to the circumterrestrial case, but also to space weather science in the entire solar system. The space weather is the physical and phenomenological state of the natural space environments. And already by this definition, one can understand that to understand the space weather conditions around a planetary body, either the Earth or any other planetary body in our solar system, we need to reveal the properties and the details of the interactions between this environment of our interest and the space that it is around it. So when we study space weather, we cannot disconnect any phenomenon, any effect that we are studying from its temporal variability of either the solar activity, if we talk about space weather in the inner solar system, so Mercury, Venus, Earth and Mars, or the variability of the plasma, if we talk about space weather in the giant planetary systems, like Jupiter, Saturn, Uranus, and hopefully in the future also Neptune. So these are some, I cited here some review papers on this stuff, which interconnect the circumterrestrial space weather aspects with the entire solar system space weather studies. So some basic things that point out the interdisciplinary nature of space weather. So in the solar system, when we refer to space weather, we refer mainly to its sources. And the main drivers are solar flares, coronal mass ejection, and solar wind stream interactions. And sometimes these three main sources can be also, as we know, interconnected. Not always, but there is a strong correlation, for example, between the appearance of solar flares and coronal mass ejections. And here you see some very paradigm features. On your left, you see the solar X flares of a specific event on 2000 or 7 June. And on the right, for the same event, we see a coronal mass ejection. So these are GOES observations from the one side, and the coronagraph of NASA SOHO's images on the right side. So these events, these kinds of events, many often are connected with other type of events, not photon emissions, but solar energetic particle emissions. And on this slide, you see two classes of solar energetic particle events. The one on the left are the impulsive events, which have specific characteristics, for example, a very abrupt increase in the flux. And the last for a smaller time period with respect to the second class on the right, which are the gradual events, which are most harmful, for example, for the technological point of view of space weather. And of course, there is a third class, which is a mixed class that contains characteristics of both categories, a hybrid class. So in reality, there is no clear distinction between these events, which complicates a little more our life and our scientific job, since we cannot always categorize these kind of events and consequently create our models in a certain way. Very often, as a result of this kind of events, we have also ionizing radiation, which can provoke also modifications in the ionosphere and upper atmosphere of a planet. And there are several review papers, as Yusoskin et al., and also references therein. And sometimes they can cause effects even at ground level, even in the Earth case. And exactly on this, I would like to cite also this paradigm that shows the flare event here on the left side and the coronal mass ejection event of a specific phenomenon that took place on the 17th of May 2012. And these emissions, these sources of space weather on the sun were accompanied by a strong solar energetic particle event that you see there, registered at L1 by ACE, and also by the geosynchronous satellites, GOES. And this event included also a relativistic tail for the energetic particles, and these high energy particles above almost some hundreds of MeVs per proton cause also a ground level enhancement event, which you see here on the right. These are not primary particles. These are secondary particles provoked by primary particles which were energetic enough to pass the magnetic obstacle of the Earth. It doesn't happen all the time to have a ground level enhancement event when we have solar energetic particle events, but sometimes it does. And this puts another piece on the space weather chain from the scientific point of view.
So there is an extensive shower that measures.
Exactly. And the way it is registered on the ground depends also on the station and its location. Different on the pole, for example, Antarctic, or when we go to cutoff rigidity near the equator, of course, we need more energy for the particles. So there's a strong correlation, of course. So in this figure, you see the variety of events we have when we talk about space weather, that in reality include very many different sub-disciplines within what we call space weather science discipline. So we need to know things about galactic cosmic ray physics because we need to know the background above which the particles can be registered, the particles of solar origin. We need a lot of knowledge regarding solar physics, the evolution of magnetic fields, the generation and the propagation and acceleration of energetic particles, the flares, the CMEs, the various emissions from the different layers of the solar atmosphere, solar wind generation. Then there is all the propagation part, and then there is all the interaction between what comes, coronal mass ejections, particles, photons, with the Earth's magnetosphere. And even within, what happens inside the ionosphere, the atmosphere, eventually also at the ground. So geomagnetism. And even if we go a little further, there is a whole topic that regards the effects, technological and biological, when we talk about astronauts, of space weather. And this is an entire discipline that also has to do also with life sciences. So space weather science is not only heliophysics. It is largely based on heliophysics, but it is not only heliophysics. It has to do with planetary sciences, earth sciences, life science, material sciences, and other topics that I have not listed here. So inter and transdisciplinary field of research. And of course, there is all the operational part that as scientists, we may not care too much, but there is a strong technological interest here, economical interest, and there are these passages, research to operations and operations to research that can bring from both sides important and very useful feedback. And of course, the research and development of payloads to monitor space weather, payloads and facilities, as we heard today here. So how connected is heliophysics and space weather in Europe? So as I said before, we have many, I talk mostly from the agency point of view, so I focus here on the payload development. We have many instruments that make part of heliophysics or solar system missions. So we have many teams in Europe, but also in the US and other countries that we collaborate in order to develop nice payload instruments to have our observations in the different fields of space weather. We have different international projects as the ones that were cited before, and we have H2020 and other initiatives, many EC groups that focus on the scientific part of space weather and heliophysics, and we have many facilities. We heard very many things today on this part in Europe, dedicated to space weather monitoring or forecasting, or even to pure solar physics science. And we have different sessions in various meetings. EGU is a very good place where we usually meet. There are many sessions that are split across solar terrestrial, planetary, solar system science, operations, space weather. etc. And we have our annual meeting of the European Space Weather Week, which took place less than a month ago. And of course, we have all the strategic part, for example, like the European Space Science Committee with the Solar System and Exploration Panel, which treats also space weather. And we have the panels in the European Union and other stuff like the COPUS working group, which finished his work 1 year ago. And we have also an internal ESA group on heliophysics, which did a very nice meeting last month in ESA that we talked, we exchanged feedback with the colleagues, and we had beautiful and nice ideas for the future. And many other things, for example, like the ESA safety program. And in Italy, we participate in all this stuff because we like to have, and we do have, a strong link with international activities. Also the ones that you develop here in Sweden, but also in the other countries. And we participate in very many different projects and instrumentation stuff. And I would like to point out in this list also the fact that ASI some years ago tried to put together all our efforts we have in the country and created this ASI Space Weather Working Group, which worked for almost 2 years, maybe something more. And what we did, we included several colleagues, several scientists from important institutions in Italy. And we did a study and a work on understanding the state of the art of space weather science in Italy. So we wrote an extended paper on this in order to bring together what we have in an entire document. Practically, it was a refereed paper that we published in the Space Weather and Space Climate Journal. And then the most important part, we tried to put down our perspectives, what we want to do in the future, why do we want to do it, and how do we want to do it. And among this, the most important part of this, let's call it roadmap, this perspective work, was the development of a scientific space weather data center, which is called ASPIS, which in Greek, by the way, means shield. So, ASPIS, here is the team. I am the project scientist for ASI, for ASPIS. We have Anna Mililo, who is the scientific responsible for INAF. It's an ASI INAF project. We have Giuseppe Sindoni, project manager, Alberto Bigazzi, that supports the project management activities. And we have some other persons who work on a specific project that I will cite later from INAF, Monica Laurenza, Dario Del Moro from University of Tor Vergata, and Marco Giardino, Gianluca Polenta are the persons from the Space Science Data Center of ASI, where ASPIS will be installed. So what is ASPIS? ASPIS is an ASI INAF project pointing out the development of the National Scientific Space Weather Data Center. I underline this is not an operational center for space weather. This is a scientific one. It collects data, models, documentation, and tools. So through ASPIS, it will be possible to explore, visualize, compare, and analyze a great variety of data and products, which the community already has, but until now, they were not collected and gathered in the same place. They were not, let's say, that easily accessed. This is a work that already the Italian community has done. And in this way, we would like to have this let's say, database extended. It's more than a database because it contains also a model to have it all together under the same umbrella in order to be able to interact also with the international community better. So this will help us also to prepare applications for the future, but also to support activities of robotic and human space exploration in the future. We have 2 nice papers on ASPIS and on CESAR. CESAR is the first project that is responsible for the implementation of the first part of ASPIS. The project has started some years ago, 1.5 years ago almost, and it will be finished in this spring, hopefully. Then we will have the first beta version of the center. So here, ASPIS, the reference point that collects data, images, science product models, and it will also treat some specific science cases of studies and documentations. These are the different fields that will be included. So we have solar physics data and models, solar terrestrial physics, geomagnetism, physics of the ionosphere, stuff, and the planetary space weather we treat for initially Venus and Mars. But we will go also further to treat also the Jovian system inside the physics of space weather science, inside the Jovian system, very useful for future missions, for example, like the JUICE mission, that here in Sweden there is a strong contribution from ERF. And then also galactic cosmic ray physics. So SPACE is a research project that creates synergies. It will create synergies in space weather science among different communities, favoring exactly knowledge exchange and collaborations, which is what science, in my opinion, should always do. So here you see a more graphical part, the presentation of what a SPACE will be like, interlinking the 4 more important nodes in this ecosystem of space weather: research, observations, services and operations, and payload development. And challenges and synergies and inter and transdisciplinarity will be highly favored through this effort. So, okay, so here you see the main outputs of the projects that are expected: science products related to the original data to be further used in other situations, and a really broad set of parameters in the space weather domain. And we will try to make this very user-friendly, this environment, also to favor, let's say, the studies and the activities of the younger generations. We want to create the next generation of space weather scientists in Italy, and hopefully also in collaboration with the international teams. And all these things will be coordinated within this environment. And at the same time, we would like to provide also test beds for forecasting models. So we are not an operational structure. This is not an operational space weather center, but it will be useful for the models. In a few words, space weather research from a larger perspective. And this, of course, can work as a good link with international scientific community, in our opinion. So this is a little bit of history, how the whole thing started from the ASI Space Weather Working Group that created the roadmap. And then within this group, we defined some science cases from which we wanted to make this effort begin. And then we defined a team. We issued a call. There was a national call that all the teams in Italy could participate. And a proposal won this call. This proposal was called the CESAR. This project is actually under implementation this time to create this first part. This is the CESAR slide. PI is Monica Laurenza from INAF, and Deputy PI Dario Del Moro from the University of Tor Vergata. This is the executive board team that I mentioned before. So the objectives of CESAR are the same, of course, with SPACE, to provide all this data and the modeling tools and to advance our knowledge and to design, implement, and populate with the products that already the community has this first prototype. So just for some statistics, 11 Italian institutions, including 92 researchers. We have several calls also for young researchers. We have several students that participate. And we would like exactly to be able to give our contribution through research activities to this chain of the space weather. So to cover the entire part of the chain: sun, interplanetary space, Earth and planetary environments. So really an interdisciplinary and integrated approach in research. And I finish here. These are 3 very recent posters. I know you cannot read, but I can discuss with you when you want, also through email. These are three contributions, as I said before, to the Space Weather Week. This was a very nice meeting that our colleagues in ESA organized in October, November, some weeks ago. And this is the part from CESAR, which is a science case specific, a specific event with all the effects it had in various subtopics, let's say, of the space weather science. So I leave you here with my concluding remarks, and I thank you for your attention.
Thanks, Christina. Questions? Please again.
Yeah. So can I talk also here? Or, yeah. Okay, this is as I passed it a little quickly. Here it is. This is the part that you're asking. We had created this working group, this strategic working group that worked on all our stuff, and then we issued a call that we funded as an agency. for proposals for implementing this first version of ASPIS. And the call was treated by Asi and Ina. We had an executive, a very big selection team of reviewers. Of course, all the people that didn't participate in the proposals, but from the entire Italy, we tried to do it as well as possible. The idea is to have a next call, yes. Yeah, okay. The thing is that now we have this ASPIS project that is being implemented by the CESAR project. The CESAR project will finish. So as an agency, we have to understand how we are going to move on. The idea is to give a continuation in this, but still I cannot say nothing for sure. But the idea, there is a strong interest. This I can surely say.
Okay. Any more? I don't see. So if there are no other questions, we can go to the last speakers, which is Flavia Carrozzi, that will talk about again science. And he is now at the Chalmers University, and his contribution will be on low frequency from high latitude. I'm not. Please, the floor is yours.
Thank you very much.
Yeah. Yeah, I can. I know how to do it. Control L.
Yes, that's right. Yes, thank you. Yes, thank you for the invitation to speak here. And apologies that our director, Unsola, could not come because he was originally envisaged as being the person to present this, but I'm the stand-in. So yes, my name is Flavia Carrozzi, and I'm at the Unsola Space Observatory. And I thought this is a good opportunity to talk, first of all, about what Unsola is, because not everybody knows what the observatory in Unsola is. It's a infrastructure for radio in Sweden. So basically, usually it was radio astronomy, but we've been now looking towards other applications. But it has a long history of going back already after to the space age, beginnings of the 60s, where we had the 25-minute telescope. This was the first transatlantic, where we measured the first continental drifts with this telescope in the foreground here, between the North American continent and the European continent. So we do also geodesic geodesy. The first measurements were made with this telescope. Then in the 70s, we built the first millimeter telescope. Nowadays, it's not a big thing because there's much nicer places. And then towards the last decade, we've been running the LOFAR station, which in this picture you can see just barely is being constructed there. So that's the progression. We also have other telescopes and infrastructure that facilitate and support radio astronomy, in particular in Sweden and also in the world. So yes, we're on the west coast in Gothenburg, outside of Gothenburg. And we are what I'd like to talk to you specifically today about is the LOFAR, which is a low frequency array. And as an array, then of course we consist of many stations across Europe. It's called international because it sounds, of course, a lot nicer than just say that it's Europe. But mainly it's all in Europe, basically. And this is a map of the different stations. We have 52 stations across Europe. We've been there since the beginning. Recently, or very soon, they will also build the one in Italy. Now, the frequency range is between 10 megahertz and 240 megahertz. So it's much lower than what we've been looking at. But there was some images, and LOFAR images have been shown here at this presentation in this day already. And the reason it goes down to 10 megahertz is because nothing below that can be seen from the ground. because of the ionospheric cutoff. So below 10 megahertz, you can't see anything. So this is really the lowest frequencies that can be accessible, the window on space that can be accessible from the ground. You'd have to go to space or the moon to see below that frequency. Now, there's basically two observation modes. I don't know if you can see it because it's fallen off the screen here, but either we use it as one collective array, which then becomes a huge, one of the biggest telescopes in the world in that sense, because it then works on thousands of kilometers. But we can also bring out one station just to local, what we call local mode, that you can only use that station for observations. Now, the Swedish station, so I'm zooming in on to the Swedish station, of course, we had to build it in the KS style. And this shows you how it was made. So there's 96 low band frequencies, that's the lowest band. And then there's 96 higher band arrays. The division was originally envisaged for the FM band, because the FM band is around 100 megahertz. So the low band covers below 100 and the high band covers above. And then there's one container. And here you can see the actual picture of the site when it was completed about more than a decade ago. That's the LBA on the left and the HBA on the right and the container in the middle. And all this is then either sent down to Netherlands, which is the central core, to become through interferometric correlation, then we can make interferometric images. Or we can use this as a standalone station to do science locally. And of course, we're not above the polar circle, but we're at 57 degrees north. But we're one of the most northern state, in fact, the northernmost station in the network. So locally, we've just in the last few years become just doing more and more space weather-based observations. And this is the sort of stuff that we can do with our local. Well, this is Aurora actually just a few last week above the Onsala. This is the radome of the 20-meter dish. You can see, I think, the Aurora in the background. So it's actually Aurora all the way down to our latitudes, in Gothenburg. And we even can do things like lightning and air showers with our local station. This is all in the radio frequency bands because we can do imaging. And of course, there's also spectral, where we can do solar burst type spectra in full polarimetry. And when we go to the other extreme, where we have the whole array, then we can do a lot better imaging. Then we can actually image the sun. And sometimes you see these blobby images of the LOFAR. That's because these are low frequencies, of course, and sometimes you don't really trust that these are actual images. But here's a convincing image because it's the eclipse. There was an eclipse a while back, and this is the imaging just before the moon goes across the sun. And these are different frequency ranges, and this is during all the partial eclipse. And you can see very clearly that the sun is coming out after the eclipse. So this gives you a convincing, even though it does, if you were to look at this image, you wouldn't say it was the sun, but this is at the radio frequencies of that, but this convinces you that it actually is working. So in the last few years, as I said, we've started now to look more, because traditionally we do radio astronomy. We're looking more at things like collaborating with others to do solar and to do space weather type observations, because radio can still be used for other purposes than celestial objects. So the operational modes that we were looking at together with ESA and with Astron is that we can have typical scenario is that you have nighttime observations of astronomy. But during daytime, you can do things like looking at the sun. And in fact, at noon, local noon, we can do, they do imaging of the sun from the central core. And besides that, we can do simultaneous, this topic of calibration was brought up, how difficult it can be to do calibration. We can do with LOFAR, we can do calibrations toward Cassiopeia A almost simultaneously because of the the electronic steering rather than the parabolic dish has to slew. But with the LOFAR, because it's all phased arrays, we can do simultaneous calibration on Cassiopeia 8, for instance, as a calibrator, and do then calibrated images of the sun. And then we've also collaborated on more to do bursts, and we're looking at machine learning there to categorize bursts when there are bursts and trigger other monitoring schemes. So if we detect a burst, we can do different observation, change the cadence of observations. And one very interesting topic that we've been exploring in the last few years is the possibility of tracking CMEs. You know, that Peter was mentioning this. The idea here is that if you have a CME, well, we typically look at pulsars, which are radio beacons that are fixed to the sky. And as the CME approaches the Earth, with tomography, we can monitor these the Faraday rotation of the pulsars, and if we see a huge shift in the Faraday rotation depth as the CME passes through, then that's a detection of the CME, and potentially also using the Faraday rotation, we can also establish the magnetic field along the line of sight. And this is like the holy grail of that we could do CME tracking and also determine the magnetic field of the CME, because that is when things you get an interaction with the Earth's magnetosphere. We're also looking at collaborating with there's an outrigger of the LOFAR, which is technically speaking exactly identical to the one in Sweden, but it's up in very close to the S-range site. It's called Kyra. It's actually geographically in Finland, but we've been collaborating with them for some time, and they've been actually doing space weather monitoring in the whole 10 years, because they're not part of the actual ILT, the International LOFAR telescope, so they can dedicate 24/7 observations on the sun. And we've been, and this is the sort of data that you can get from that station, where they have all sky imaging to do ryometry. They can do spectra to look at bursts. They can't do imaging, of course, but we are planning on looking at using potentially the Sardinian Array Demonstrator, which is the SAD. They have, which is not being employed right now, but to reusing those, refurbishing those, and bringing them up to Kyra to potentially be able to image with longer baselines the sun. And for the future, as I said, we don't do that much space weather, but that's because we typically do radio astronomy. But for the future, there's something called LOFAR 2.0, which will double the bandwidth, but most importantly, will also allow for a second beam that will be dedicated potentially for space weather applications. So they won't have to interfere with each other. One will be running, looking at the radio astronomical targets, and the other one could be dedicated for looking at the sun and scintillating sources, etc., to do ionospheric work. And that's been, the first prototypes are already been built, and it will be rolled out next year. And so that's an exciting time now that we're looking at expanding the operations of LOFAR to go to solar and to space weather. So in conclusions, yeah, we've been operating now for 10 years and more, and it's mostly been radio astronomy, but we're looking at doing space weather in the future, and there's lots of interesting things that we are collaborating with to make more data products available And yes, and we also have these plans of expanding with the Kyra to make images potentially above the polar circle of the sun, which could be of interest to the Solaris, but at the lowest frequencies. The idea there would be that we were using these outriggers that might be these Sardinian array demonstrator. They have these 256 elements that are deployable independently, and they could be placed at the Kyra site to improve the UV coverage, as we call it, the ability to image the sun. And that's all I had.
Questions? Me? No. I mean, it's a real pleasure. I mean, there is no limitation. You can do even 3 questions.
There is a CME launched.
Yes. Yes.
How fast can react to
Yes.
track it?
How fast?
Yes, I mean, you want to have, let's say, a prediction for arrival.
Yeah. Well, again, this is very bleeding edge technology, and it relies on having pulsars in the right place. But there's a growing catalog of pulsars, and it's been tried. And I wouldn't venture to say what sort of time or anything like that. But it's still at the bleeding edge, and it's being worked on. It works, but it needs more work.
3 hours or?
Yeah. I mean, it depends all on the morphology of the CME, of course, and on what pulsars we see. But the idea is, to track using pulsars. There's lots of pulsars along in the ecliptic, and as the CME comes out, then we can see perturbations in the Faraday, rotation measures of those. So we would see that as it escapes from the heliosphere.
Then the magnetic field.
The magnetic field comes with the Faraday rotation. Yes. It's actually what defines the Faraday rotation. Yeah. So and the differential. So if you're tracking it and then suddenly you see a change, the Faraday depth will give you the magnetic field.
Intensity or
the intensity of the along this line of sight. Yes. Yes. You need to polarize.
So thank you for the presentation. Christian Hansen from SCC. Not so scientific question, it's more curious. The sites for the LOFAR, were they placed there, or did you just put together already existing ones, or have you constructed it to create this? I'm comparing it, for instance, to the Square Kilometre Array observatory. It's not to say you used what is there, or you have okay.
So these are existing facilities, basically. In the Netherlands, that wasn't the case. In the Netherlands, they originally built all over the place in the Netherlands. Ironically, they suggested, we will put a facility, a station there, and you will get a high-speed broadband internet connection, because this was around 2000. Now it's all over the place, but at the time they suggested this as a way of rolling it out. But yeah, it's in existing facilities already, if that's the point, yes.
Christine.
Also, thank you for the nice presentation, and it is really nice to see these perspectives that an instrument initially designed for other type of science to be brought in the solar physics and heliophysics science. I think this is very important also from a larger perspective. So my curiosity was, in the future, when you will have this solar data with LOFAR, have you in mind to do also some kind of study post-event, of course, using also other types of data, for example, particle data, in order to bring constraints to the models you are going to create on the basis of the LOFAR data? So this more integrated approach, do you have in mind something? Can you comment?
Well, we're going basically from right now it's science based, so we don't have like we're not a forecasting center, something like that Peter or you guys would want to do. But we're working towards that with these collaborations, with these idle projects that I showed. We're working towards making products that will be used by, for instance, things like that you're putting together. Yes, and then we would ingest these, and they could be used in collaboration with connection with particles.
Yes, second step.
That's right. That's right.
Thank you.
So if there are no other questions, I think I have to thank all the speakers. And then I would like to make closing remarks, and I would like to invite Wilco to have some comments, and even Gunnar. Then I would like to make the summary. So Wilco, please.
Yes, I just want to thank you all for coming, and I think it has been very interesting to hear all your presentation, and very exciting to see how this will go forward with Laris, for example. If we will see you here in Sweden later on. So thank you very much from SNSA for coming and joining us here today.
Please.
I think that this has been a great experience for SSC to the pleasure to gather you all here. It's been most interesting to listen to the thrilling story about space weather and the effects of the sun. I get a little bit nervous when I see all these flares, all these ejections, all the consequences on Earth, and I realize we're going to a society that becomes more and more sensitive for disturbances, and therefore, indeed, even more important to study the sun and predict such events beforehand. Very important. I thank you all with the patience also for the presentations and learning things that I should have known before. So but thank you everyone for that, and thank you.
Thanks, Gunnar. So I would like to close with just a few comments. Of course, I will acknowledge later, but let me say it was very fun for me because I'm not a solar scientist, but I know that there is a lot of connection with everything, and then I would make a couple of comments later. So I have to say that it's very interesting that there is a bilateral interest. So we are making discussion on something that is interesting to both of us, and that is already a success for me because it's not easy to find common point, and I like it. And I think that in particular in the second part of the meeting, I discovered myself that there is a huge scientific interest, which is not only associated to the fact that we do science, because we're born to do science, but also there is a very interesting part in terms of technological platform, because this range is fantastic. I think Sweden is still unexplored, the potential of this range. And let me just say that around Kiruna there are fantastic things. Well, for example, we just talk about a little bit about extensive shower. So in Kiruna you have a mine 2 kilometers deep, already equipped, just plug in to put instrument to make detectors, to install detectors and see physics coming from the sun, from the cosmos, and it's there. It's just to plug in. And that's it. When I went into the mines, I say that's a fantastic place to do any kind of science, and with X-ray, with the radio wave, and with anything you like. And you have even the mobile connection already done. So, I mean, for scientists, it's a need.
By the way, so I think there is many things to do in terms of science, but in terms of technology. I was already astonished by the fact, okay, we need artificial intelligence or machine learning or whatever you like. But I think we first to start with the normal intelligence and then go on. But anything that can help us, it's. I recently read about the cosmic artificial intelligence. So it's not to study cosmic rays. Would be fantastic. So I think it's very important what we did today because I want to underline there is another project that we are evaluating with the Minister of Foreign Affairs and WAR. I invited WAR, unfortunately no one from WAR could come, but I think the discussion will go on and I expect I will be happy if one of the projects in this field will be approved and there will be of course possibility. But I think the main message is we need to enhance the cooperation within our countries and within Europe, please. So we need to do better and really effort to work within Europe. That's fundamental. And then let me joke for a moment because when I switch on television, I see many weather channels. So maybe in the future we will have a space weather channel, which is probably high-tech relevant and with a high price to be informed of what's going on in the next. And then it seems stupid, but it doesn't because the main event that Gunnar worried about was in 1859, so 100 years before I was born, and it was extremely huge, but it was not technology. If the same event was occurring now, the Carrington effect, I don't know what's going on to the technology of today. And let me say that Tesla has to be taken care of. So I don't want to go on. I think the time is over. And thanks. We are in time. Yeah.